Now we'll be going into the overfitting model in today's lab. So what we are going to do, we are going to take a data set. We are going to practically see how overfitting will happen and how to come out of that overfitting. That is what we are going to discuss in this today's lab, right? So can you see my collab screen here?
Yes, sir.
Yes.
Sir,
Okay. Let us start
Yes, sir.
another collab thing. So what we are going to initially do is we are going to have a particular kind of data set that is going to predict house price. Right? Based on that house, that is house price can be on many varieties. We are going to take a normal linear regression and try to make overfit for the house price data. I can have any the regression takes place there, and how the regression is modeling that house price. We are going to see it practically, right? So we use the same kind of code here, not much innovations here initially because we know how to do regression. So the thing is how overfitting will happen in practical. So let us see. We need import pandas. I need pandas for data set trading. Import pandas as PD. Next, I need NumPy also. Import NumPy as NP. Next, I can use matplot lib.pyplot, or I can use cbon. I can use cbon also. Anything I can actually use for the plotting. Let me show you both matplot lib.pyplot as PLT. Next, import cbon as SMS, alias, right? So these things I'm going to have, and I need to use linear regression. So I use import sklearn dot linear underscore model. Scale input sklearn dot linear underscore model. Why my suggestions is not coming here? Linear model from from sklearn dot linear underscore model. Import linear regression. And I need to do training and testing. I want to split, so I have from sklearn dot model underscore selection. Import train underscore test underscore. So far we need these packages. Once these are ready, I can actually proceed. Right, so it is working. Now I'll move to my data set reading. Now I need to upload the data set. I will post you the data set link also. I have taken that from Kaggle. Uh, I'll post you that link also. And this is the link of the data set actually. I just put it in the chat box. You can take that from the chat box. That is California housing data set. You are having download 400 KB. So I'll also upload here. I have already downloaded it. So I'm having my data set will be housing. Uh, so housing.csv is loading for me. Once it is completed, I'll use the pandas to read the particular file. Right? Shall I take the data? df for data is equal to pd dot read underscore csv, and I'll put housing.csv. My data is ready. Okay, now I'll proceed. Now the main thing to understand is data cleaning, right? Let us see the data df.data. Now if you see the data, see what is available: longitude, latitude, housing, median age. What is the median age of those people? Those residents or those people houses age, and total number of rooms in that particular locality. 880 means that there may be more than 100 or 200 houses there, and each house may have those many number of rooms, and this is the cumulative room in that particular locality, and the total bedrooms, total next population, household, median income, everything. The total rooms in the sense it will include kitchen, hall, everything. Bedrooms will include those only. Sometimes house will have single bedroom and so on. Then number of households, total population, and median income of those people. And here, this is what the value to be focused: median house value. So the median house value for this kind of people is 4,52,600. And what is the area is the area near bay, that ocean proximity is near the ocean, near bay ocean. It is actually this particular price, right? So this is the data we are having. But if you completely see this data, I'm opening this out and using that CSV in Colab. If you completely see this data, since I did this practical before itself, I found that there are many NA values available here. I'll show you those. Many NA values are actually available here, and there is a need to remove those NA values because it is actually a very big data going into 2068, 2064 pages till now, right? You see here, many values will be there with dashes and something. If you go there, the housing median age will decrease, and sometimes it becomes even more less also. And if you see 1.7 in one place, median income, and in one place it will be more, there may be more number of outliers also. So what we have to do is we need to do a proper cleaning. Data cleaning is actually needed. So that is what the next task will be going for data cleaning, right? I use a function data cleaning. Now we are going to go in the next step. Hereafter, if you go for any data set cleaning, we can use this function. This function is actually responsible for removing number one, NA values, number two, high longitudinal values. High values in the sense some values will be very large compared to the other values. Surely they require normalization. Our computer may consider it as infinite values, and there is a need to reduce those kind of values. So because those values cannot be converted into floating point values, all the regression items will work on floating point numbers. So we need to remove those kinds. For that, what we will be doing is we'll be doing some data cleanup. So hereafter, if you want to remove NA values and infinitely large values, you can use this cleaning function. So I use clean underscore data, clean data function, and this clean data function takes an argument as df. And I'll pass the df to here. So what are the things it will have? If the first one, right? What we have to do is we need to convert this df into a data frame, right? So what I'll do, I'll try use an asset function. This asset function is actually an info function for my Python program to say that this is going to be converted into a data frame, right? So I'll take this instance of data frame to pd dot data frame. I convert into a panda data frame this. Mean go with the suggestion data frame, capital D and F, comma. And what are the other things I have to do? Df dot drop NAs. So drop NA values. So I can drop the NA values here. And if NA values is in place, I make true in place in the sense if in a particular cell NA value is there, I'll remove the entire row. So far we will be doing that. If you want to do some other operations like instead of removing, I can replace it with some other values. That also we can do. For this current way, what we are going to do is we are going to delete the entire row. So that is with respect to drop NAs, right? After dropping NAs, I need to keep, I need to remove the infinite values also. So I go, what are the values I need to keep? What are the infinite values available? I have to remove those infinite values. So infinite values may be available in some columns, which is having a highest number of things, and some columns are very big numbers are available, right? So those index I need to remove. I'll take index to keep. What are the index you want to keep? Index to keep What are the index you need to keep? That will take index to keep will be df dot is n np dot nan should be considered, np dot inf should be considered, or the minus np dot inf should be considered. Any of the one should be considered for keeping that particular index. So I'll do that. And these things should not be there. What are the things should not be there is np dot na nan should not be there, np dot nan should not be there, and np dot inf should not be there, and negative infinity also should not be there, minus np dot inf, right? So this df dot is in or in np dot nan, np dot inf minus np dot n. If any index is going to have this particular value, any one of this, if I want to say any one, I'll put dot any of one. If any one is actually there, of these three, if any one is there also, what I should do, I should not keep that particular index. So this particular value will give me an index with NA values or infinite values or negative infinite values. So I want to take negative of this. I don't want this these indexes to keep. These are the indexes to discard. So what are the indexes to keep? Just to put a negation. Just to put a negation, and these indexes should be removable. Just to put a negation. Next, what I do, I return df. I return df. What are the df should be written? Index to keep alone. Other indexes I will neglect. Index to keep alone will be kept, and other index should be removed. And what I will do is I will convert everything into floating point, because regression actually require everything to be in floating point. So np dot float 64 bit. So in this way, I actually do the variation. Right? Run this definition. I have an error. Let me check what is an error. Okay, if I get this, I need to give some information. Uh, df is not a data frame. If I was giving a df and df was not able to convert into a data frame, then I should say yes, df is not a data frame. Like that, I need to display. Now my function is ready. This is a clean data function. Now what I will do is I'll open another cell and I'll call. I am now already having the df ready. This is the df which is read. Now I'll send the df to this cleaning operation. I'll put a comment also here. Clean the data set. So df is equal to clean data of df. Now data is cleaned. Let me check again. Now we get another. Could not convert string to float nearby. So okay, one of the values is actually having that particular entity, right? So we don't want to convert that. We can take because this is actually a string which cannot be converted into a floating point number. So this cleaning we didn't do. So hope you understand what is the error. We having something like nearby, those kind of stuffs here. Those are string values which cannot be converted into a floating point number. So we cannot clean those. So first what we will do is we will take the data what we actually going to analyze. We are going to take total number of bedrooms, and based on the total number of bedrooms, we are going to predict the median house value. The linear regression between total bedrooms and median house value. That one we are going to take. So let us take those two DF alone and then clean the data set. So I will take DF is equal to in the housing data DF. I'll put an array. Inside, what are the things I'm going to take? Total underscore bedrooms. I take the exactly the same name that should be used. Total bedrooms and median house value. This is a median house value which is going to be analyzed here. So these are the inputs what I'm going to input and output what I'm going to analyze. Yes, it was need to be in double quotes. Yes. Now this is the thing, and we got the data clean. Right now, the data is very clean. Now we can go for the next steps in regression. So now the clean data is done. Now we can go for scaling. Why I'm doing scaling here is now I'll print the df for you. I put df dot head. I put df dot head. If you see, I'm having 129.0 here. On the other hand, I'm having 452600. One is x-axis is very small, but y-axis is very large. So the predicted value is going very large. So what I can do is I can scale them in such a way that both are actually looking somewhat closer. So that scaling need to be done. One of the scaling operation, what we can do is take log. So if I take log, all of them will come closer to zeros and ones. And other thing we can use is we can use min max scalar function available in scalar. We can use that scaling one of the pre-processing operation. So from SQL done dot pre-processing, we can use min max scalar, right? So by using min max scalar, we can actually do that particular scaling processes. So we will do that scaling now. Scale the data. So in scaling the data, what we will do, we'll take the columns first, df columns. I'll convert everything into columns. Now it is in data frame way. So what I said, df dot columns. So I'm having in here after it is not be going to be defined as df alone. I take it as df dot columns is equal to d. In this data frames, I take the columns. What are the columns? Is total bedroom is one column, median house value is another column, and I can now scale it. I need to include a package here that is from sklearn dot pre-processing. I'm going to do some pre-processing here. So import min max scalar. And sklearn dot pre-processing import min max scalar I need to use because I need to scale my particular data. So okay, this is done. I'll come down. So now I'm having df underscore
Sir,
column
sir,
is
one shows that.
yes. Once I want to show the min max scalar,
Ah, sir.
yes, I put all the sklearn packages we downloaded in the chat box. Shall I move on?
Yes, sir.
Yes. So now I will use the min max scalar here for my df columns, and I can directly do it in df and then substitute here. So df is equal to scalar dot fit of. I can so scalar actually in object came from the min max scalar. I can actually define the min max scalar like scalar is equal to min max scalar of. Yes. Scalar is equal to min max scalar. Df is equal to scalar dot fit, right? So fit underscore function. So now my df is actually scaled. Now the values will be somewhat very closer. If it is very small, it will be 0.000. If it is very large, it will be closer to 1. 1 means that the highest value. So instead of not, I'm doing like a percentile calculation. That is what the scaling operation will actually do. Right? Now I again convert that df into data frame to ensure that it is actually looking like a table. 3d dot data underscore data frame. D capital and of df. Yes, now it is actually being scaled up, and I can also print and see how it is actually being done. Now again, I need to ensure this df columns is actually being updated. Let me do df columns because this df is actually different. After scaling, df actually changed, so I can update this df columns. This is actually not needed then. Then after that, I can print and see my clearly result, and I need to do some df dot head of here. name, index, total bedroom, or in columns. Index of total bedrooms, median, details, or in columns. Let me check with the previous way. Once we done this, here I come here, I execute this column. Yes. Now I got the scaled value, right? My scaled value, see my total bedrooms here, and one is nothing but the housing price, right? So the house value. So those were actually described here. Now let me run it on the whole and see error results. When I run it on the whole, error actually comes. So the problem with this converting into the scaled value or running
Sir,
it.
column names are changed, no sir.
Yes, yes. Arguments are changed. Now it should be zero and it should be one. When it run types, this should be zero and this should be one. Okay. So I again run it up. But I don't want the argument to be changed. How can I do that? Let me retain this df uh, I'll transfer the column names in the name for df columns, and now I test df dot columns is equal to df underscore columns. I think now I can get the column names also. Now it's taking time to run, but I think this will work. I'll just transferring the column names
Yes, sir, it worked.
initially. Yes, it to df columns, and then transferring the df column names again to df dot columns. This will surely work. Like I am, it's taking time for me to run. Okay. Yes. Total bedrooms and median house values are retained. Now going to the next where now we need to go for changing the array size actually. Now I can actually print and see how the visualization is actually going on with respect to x and y. I can just plot and see how x and y are actually depicting. I can just go for plt dot scatter. Plt dot scatter I can do, or I can go for SNS also. That is Cbon. Right. So what I can do, I can visualize the plot and see SNS dot regression plot of, and x will be total and y will be median underscore house underscore value. So now we are going into now this is the input plot what we are having. Now we are going to apply regression for this. And one more thing what we have to do with this regression plot is this regression is actually need to be split into training and testing. We use the same 70-30 way of thinking. Then we do some reshaping because we need to give data like n cross 1 to the regression, but actual will be n cross something because n cross n also can be there, or n cross 100, n cross 200, like that it will be there. We need to give like n cross 1 only. So we need to do a reshaping for that particular data. Now what we are going to do is we are going to do a train test split into training and testing. So the first say, so I'll take like X train, a Y train, or DF train, anything I can take. DF train, DF test is equal to. Instead, I'm separating into training and testing because I didn't separate into input and output like X and Y. So far, it is total bedrooms, median house value alone, right? So now train underscore test underscore split of the entire data set BF. And how I'm going to develop is train underscore size. Say train size is going to be 0.7, 20 percentage for training, and the test underscore size will be 0.3. And I kept random state here also. I want randomly to be splitted, so random state will be 10. So this is now the training and testing is being done. Sorry, training and testing is being splitted. Let us also print and see what is the length of training and testing. Print of len of df underscore train, and print len of df underscore test. This I get around 14,303 set in training and 6130 in testing. Right, so this is the very big data we actually have, and we also need to ensure that the cleaning is done properly. Because if the cleaning is not done properly, surely we get some errors when we go have this so many large amount of data. If some missing values is there, so X test is nothing but df underscore test of, again I do total bedrooms, total bedrooms, and y test also the same. Y test is equal to df underscore test of median underscore house underscore value. Have this ready. These are actually the training and test results. Now we can go for now everything is ready for us. Now we can directly go for the regression term. We can actually take we call the regression function next lr dot fit off. But we know that surely this linear regression cannot solve it. So either we can try for a linear regression once, surely we will not get. We can then we have to go for polynomial regression, right? Or we can also combine both the polynomial and linear and put it in pipeline also, right? I'll also do a reshaping here. So we know, right, why reshaping is done. For example, I will write here why reshaping is done. Reshaping of data. We want to set the dimension. The dimension to be used for the scalar should be n cross 1, right? Right here, dimension be used for a scalar need to be n comma 1 or n cross 1 actually, n comma 1. But the data usually available maybe n comma something. I don't know what is the something. There can be n number of data, or there can be 100,000, many things can be there, but we don't know that. But I usually request n cross 1. So that we need to reshape that into n cross 1. So how to do that reshaping? I simply take x underscore train to be reshaped. So I just call x underscore train dot values dot reshape. You know that you will be doing that minus 1 comma 1. That is the thing. Dot reshape of minus 1 comma 1. So this is the thing we do. And similarly, I want to do for the testing thing also, testing input also. X underscore test is equal to x underscore test dot values or reshape of minus 1 comma 1. So the reshaping is also done. Now let us see what is the length of X train separately now. 14303. Okay, all my data are getting ready now, right? So I'll go to the next level. Here, what I'm going to do the regression. I surely know that my linear regression will not solve it. So I go for polynomial features. I take all degrees, starting from degree 1 to any number of degrees I can go. But because I really know that this kind of data set will never be predicted using a single degree, and you require more number of degrees. So I'll take as much degree as possible. Ultimate aim is what we are going to see is we are going to see how overfitting will be there, how to visualize overfitting. That was we are going to see here, right? So I'll take here fitting multiple polynomial features. Here I add another thing. Here we can do directly take the polynomial regression, or like actually do like manual polynomial things. If you want to do that also, you can actually do. Otherwise, you can take this. Our aim is not to not predict the house price. Our aim is to see clearly how overfitting will happen. That's what we are going to see. And what are the degrees I'm going to take into consideration is I can take 1 degree, 2 degree. I can have any number of degrees if you want. You can take. I take 1, 2, 3, 6, 10, and 20. So this many number of degrees I take, and all the degrees I will compute and I will use. So now I'll take for I in degrees, or for I comma degree in enumerate of degrees. Enumeration will give me zeroth value is 1, first value is 2, second value is 3, third value is 6, fourth value is 10, fifth value is 20. So the index will go to I, and the corresponding degree value will go to the variable degree. So enumerate of degrees. So that is a for loop I use. And I can take the both polynomial features regression and linear regression take kinds. So if I want to use them together in a pipeline, we have a package in sklearn to make it as a pipeline ensemble algorithm. So how to do that is I can take sklearn dot preprocessing import polynomial features. For I can import that for doing polynomial regression, and for doing those pipeline operations, I want to take from sklearn dot pipeline import make underscore pipeline. So I'm taking the polynomial features and applying linear regression on it. So I take from sklearn dot pipeline import make pipeline. Both the things I take. I'll do that. I'll go to the top. I import some other feature packages from sklearn dot preprocessing first I'll take import polynomial features. Sklearn mean polynomial features. Next from sklearn dot pipeline. So this pipeline is used to connect those polynomial features to an algorithm. The algorithm what we are going to use here is the linear regression algorithm. From sklearn dot pipeline import model dot pipeline. Model underscore pipeline we are going to use. So I'll run this again to ensure that my packages are actually working. Oh, import that this pipeline is not working. From sklearn dot pipeline. Cannot import name model underscore pipeline. Sorry. It is, let me check. I think it is, I'll try whether it will work. I think make underscore pipeline. I hope. Yes, this make underscore pipeline. So this is the two updated packages we are going to use. I'll copy this and I'll put it in the chat box. So in sklearn dot preprocessing import polynomial features. From sklearn dot pipeline import make underscore pipeline. We use both the things, and I'll come down again. Now I can use those both the features, and then I can do the polynomial regression. First, what I'm going to do is I'm going to take the model pipeline and combine both polynomial features and linear regression. So what is my model is? Model is equal to make underscore pipeline of. This is the model. And for this particular model, I can do the fitting model dot fit. model dot fit of, I'm going to take X train and Y train that are going to be fitted here. X train, comma, Y train. These are going to be fitted here. Let me check whether it is okay. Yes. So the model is fit now with my X train and Y train values. Now we need to predict and I should also visualize how it is actually working, right? So we will see predicted Y value, Y train, that is training prediction, Y train prediction, and I value, right? I take all the variables, both bedrooms as well as house price, and then the index, this particular index, what is the value is coming for this particular degree, what is the value for the second degree, what is the value, everything I need to take. Y prediction for the first degree, what is the value I'm going to take. Y prediction, so for the first degree, it will be based on model dot predict of X underscore train. Based on the training values, I can predict Y. And this I'm doing Y because this is the actual value we'll be getting. We can directly also write like Y underscore train, Y predicted value is equal to model dot predict of X train. But I'm having totally six different models here, each model taking different degree. So,
Breaking, sir.
okay. So I'll explain again. So why I put here an slice operator here is I want to take all the variables starting from the bedrooms to the value, both the things I need to take. So I put an empty slice from 0 to end, all the values I'll take. And what is this I is? This I is nothing but 0, 1, 2, 3, 4, 5. I'm having 0 to 5, 6 models I'm having. For the 0th model, what is the predictor for X train? If I use degree 1, if I use degree 2, what is the value? If I use degree 6, what is the value? Those things I need to do. So for that, I'm taking the predicted Y values different. Similarly, I do it for test also. Y test dot predict. Same thing. Comma I is equal to model dot predict of X underscore test. So training and testing is done now. Now we can actually visualize and see our regression lines, how it is actually being plotted and how the results are coming. Let me see here. White train thread is not defined. Okay, then I can actually define like white train thread is equal to 0 or something. I can create a list and say white train predict is 0. White train underscore thread.
Sir,
Yes.
white train underscore pred you given and down you given white test dot preds.
Sorry. That is also underscore only. I'll say I'll declare the white train dot thread to be a 0 list because I'm using that list as a slice. When I use a slicing operator in the list which is not defined at all, it will be giving me some error. So I create it as a list where all the values in the list will be equal to 0. Right? I np dot zeros of, and how it should be there is all the values should be 0. All the X train and Y train values should be 0. How many X values it will have is the len of X train, and about how many Y values it will have is the len of Y train, comma len of Y train. Extra bracket. This corresponds to this. Similarly, I put for Y test underscore predict. The same thing I take. Instead of training, I put test. Yes. Just I'm initiating it is an empty list fully of zeros. Now the final step is visualizing the overfit. Visualization, regression fits. I'm having many regression models here. X train, comma, Y train. So those things a scatter plot is developed. Now in this scatter plot, I need to draw a line and show how it is actually being used in the regression. Right, that regression line will be drawn with the help of the predicted y values. Right, and I can also scale it and show. So what kind of scaling I can have is I can have a plot because this scaling is for representing the y axis. Plot dot y scale. You know what axis it should be scaled is log. If I give the scale as 2, it means that it will start from 0, 2, 4, 6, 8. Like that, y axis will move. If I keep it as log, it will be going for log 1, log 2. Like that, it will be going very slow, very low level, it will be increased because our values are already being normalized. And based on the normalization only, we are going to print the data. And they'll give the title also, dot title, train data. And now I can plot everything. For all the degrees I'm having the values, I can plot all the degree values. For I in, same thing for I comma degree in enumerate of degrees, plot dot scatter of x train comma y train comma, and the data set uh, now instead of using y train here directly, I can also put y train underscore predict. What is the predicted value? I take all the values in the slice, and this is for ith model. Ith model is zeroth. If it is zeroth model, it is degree 1 model. If it is 3 model, it is degree 3 model, and so on. And I can keep the threshold S value is equal to 15. And I can also keep label. Labels will come like legend in the chat in the particular graph. Label is equal to str of degree. So in each line, it will show the degree of it. Plot dot legend of location. Where I have to keep it is the upper left. I can keep upper left in the sense in the chart it should be kept in the upper left portion. So I'll keep it like upper left. So all the data by scale is equal to log. Semicolon is double quote is missing. Yes, we have this particular thing. See, Uh, the colors is also being depicted here. And see here, this is very this is actually degree 1. If you see degree 1, it is just a straight line. There is no kind of degrees. Even degree 20 is not able to solve it, that we know. But if you see degree 1, there is just a straight line. Right? Since it is still it is not fitting anything. Even it is, if I go for this 3, degree 3 is also in a higher level polynomial that is trying to fit some kind of lines. And if I see degree 20 and the worst case, see how curvily lens it is there, how curve it is. It is covering as many points as possible. To its best case, it is covering as many points as possible. See how it is actually going. Degree 20. If you see degree 20, it will be x power 20. Like those kind of stuffs, it will be there. And still we are not, if this 20 degrees also not enough, still because these points are not covered at all. And you can also show it for the, show it the same for testing also. The testing data also, what is the result also you can see. I'll take the same thing and then plot here for testing. Copy the same thing. Instead of training everywhere, I put testing. Here instead of training, I put test. Name it as test data. Test. Now we see that I think training and testing actually overlapped. We need to separate it into two different graphs. I put subplot here. DLT dot subplot of 121. The 121 is random number giving the size. A subplot in the sense it separates both into either side, two column manner. Here also I named the subplot. This is subplot 121 and it is subplot plot dot subplot 122. We got separately. See here, this is actually the plot. Testing also like that only. It is actually minimum number of points here, trying to fit as close as possible with all the points. So now what we infer from this, if it is overfitting also, we have done enough features to get the overfitting values. See, even 20 is taken, even 25 is taken. We are trying to fit as much as possible. Now, for this, we will never say that overfitting is actually a disadvantage. Purely because even though I do overfitting, my testing value is not that much deviated. The same kind of stuff is actually available in testing also, even though I do some overfitting models. If I make it 30, it will be even more overfitted and so on. But we don't know, it will be computationally more complex. For such data, overfitting is actually useful only. But we can still do cross validation and check where actually the error actually being vanished. Those things also we can actually do. Right? This is actually the thing. You can go for any number of polynomial deviation and see. Even though for some applications we recommend overfitting to happen, because if the overfitting happening doesn't have any changes in training and testing, then I can actually support that. Here I might have see the 20th value. It is trying to overfit as close as possible, and for testing also it is doing the same kind of stuff, but still it is not able to cover many test values. The same kind of pattern is available for this particular application. Overfitting is good only because my input is not recognizing my output efficiently. So I should go for steps similar to this, right?